So we had been doing some theory part. Let's do some application this time. Let's talk about some limit computation problem, kind of like these. Limits of a certain sum, which is more or less 0 times infinity type limit. 1 over n goes to 0, and this summation goes to infinity. So basically you have infinity times 0. And what is 0 times infinity? Let's see. In calculus 1 level, most of the time 0 times infinity turned out to 0 if you use L'Hopital's rule. It's not going to be 0 anymore. These will turn out to be appropriate finite value, neither 0 nor infinity, because these will turn out to be a Riemann sum. How do you work it out? Well, first let's make this observation. This is equal to this if I change the order of multiplication. I just move this 1 over n to the right hand side. Okay, does it really help? Yes, it does. Now sine of k pi over n, we're gonna name it as f of xk, and then 1 over n, we're gonna rewrite it as delta x. Now this one is a Riemann sum. You see, with excuse me, not xk, excuse me, we need star there. Okay, we have to have some randomness here. Maybe we will have to reduce those randomness later on, but still at this moment we need some randomness. It'll turn out this is gonna be a right hand side endpoint, right hand side approximation, but at this moment we don't know that, so let's keep this randomness here. So this function, sine function, has some k expression here, and that k is running from 1 through n. So whatever that is, let's call it xk, and this is function part, alright? And then 1 over n, that goes to 0, and then the size of the partition, the width of those rectangles go down to 0, so let's call it delta x. And then all these, limit of summation, that gives you Riemann integral. Will this limit exist? Yes, it will, because sine function is a continuous function, and for continuous function, the definite integral exists. Part of it is this, the fundamental theorem of calculus. The integral exists. Okay, so much of preparation. Let's work this problem out. Okay, brace for impact. This is not going to be easy. It'll turn out that this function has something to do with sine of pi x. Oh, why? Okay, one way to see it is this. Delta x is size of the interval divided by number of rectangles, and then if we take b and a as 1 minus 0 over n, that'll give me 1 over n, which was there before. So in order to get 1 over n, we are doing this kind of manipulation, and then eventually getting a to b as 0 to 1. And then as for Riemann sum, f of xk, again, excuse me, this should be excuse me, xk is right in this case because this is right inside endpoint. Okay. We had star there, but it's okay, it'll turn out right inside endpoint. And then this is right inside endpoint value. and then this is the width of the rectangle. So this is Riemann sum, and upon taking the limit of Riemann sum, we get Riemann integral, and then calculating this definite integral, that's piece of cake. You can use the fundamental theorem, and then we go like this. Difficult to understand? You bet. It's hard. How do I make it a little bit easier to understand? We went through the theory part okay, and if you understood, great. If you didn't understand, there's still a way to handle it. Let's go to a kind of schematic solution. Here you go. Be careful, this doesn't always work, but most of the time it will work. In Calc 1 or 2 level, it's going to work most of the time. Now 1 over n goes to dx. Yes, 1 over n goes down to 0. That's interval width going down to 0. And this is basically infinitesimal interval limit size. K over n becomes x, a little bit harder to see. Let me explain a bit later. Limit of summation becomes integral, especially integral from 0 to 1. That's strange. Why from 0 to 1? But let's just take it for granted, and let's use schematic solution for this integral computation, alright? Let's move 1 over n to the right hand side and get this form. And then the color coding will help. Limit summation, that's the integral from 0 to 1. 1 over n is dx, as highlighted in red. And then k over n is x, as highlighted in green. How about the black part? They stay exactly the way. So what do you have? We have an integral from 0 to 1, sine of pi x dx. We have just integral computation to do. You can use the fundamental theorem to calculate, and then we end up with 2 over pi like this. Rather schematic, but it works. Move this 1 over n to the right hand side to get this kind of form here, and the color coding really helps. Blue part, limit of summation, that becomes integral, and 1 over n becomes dx, k over n becomes x, and what do you have? We have an integral computation. What's behind theoretically? It's because of these, but it's hard to understand. So for those students, let's use this kind of schematic solution with appropriate color coding. It works like a charm in most cases. Okay, let's keep this in your mind, and let's go over to the next problem. How do you work this one out? Excuse me, I wanted to get that schematic solution there. Yeah, okay, here. Okay, let's use this, and then let's work out this problem. Okay, let's move this 1 over x to the other side over here, and then do the color coding. This is blue, and this is red, and then that one's green. Okay, maybe increasing font a little bit, you can see this thing better. Does it look good? Okay, let's rewrite this one in terms of integral. Goes like this. Definite integral 0 to 1, and then e to the x power dx, and let's see, this is the integral part, and then this is dx, and then this should be x, not k, and that should be green. Now, did I follow this scheme okay? Limit, summation, that becomes integral, great. K of n becomes x. 1 over n becomes dx, and looks like we have this definite integral computation. Okay, exponential stay the same. And then going from 0 to 1. Alright, it's e to the first power minus e to the 0 power, so we get e minus 1. Looks like we have a solution. Is that right? Well, let's figure it out. 1 over n times over n, case running from 1 to 2n, and then n is going to 0. If I ask Mathematica to calculate this, let me see. 10. I guess I have to clear variable n because I define n as 10. Okay, that looks good. And then I asked Mathematica to calculate this one, and then I didn't get what I want. Oh, that's because n was going to 0. Sorry about that. Okay, alright. Okay, finally. I got something close, but no cigar. Instead of e minus 1, I got e squared minus 1. What the heck is going on here? You see, I got e minus 1. I got e squared minus 1. Pretty close, but not exactly right. Now, what is causing this difficulty? As a matter of fact, it's right here. The original problem, we are going to 2n. Here, in blue part, we have just n. That makes a bit of a change here. We have to go to 2. Here is a bit of a theoretical background between all these. Let's see. When k is equal to 1, that's the starting point, right? So that corresponds to starting point. Then x is k over n, which is 1 over n, and that goes down to 0 when n is really, really large. So that starting endpoint is x equal to 0. That makes perfect sense. How about the next one? N's at 2n, so this is 2n. And in that case, x is equals to k over n, right, as usual, and this 2n over n. And that goes to 2, not 0. And you have to get 2 here. And that makes a subtle difference here. Here we had just n, so if k stops at n, then you get n over n, that goes to 1, and we had 1 over here. That is not the case here. I'm going to 2n, so we have to make appropriate adjustment. That goes to 2, and we need 2 over there. What if this is 3? In that case, this will go to 3, and then we're going to get 3 over here. And that kind of computation, that kind of analogy, I'll leave to individual students. Anyway, in any case, all those are variation of the schematic solution. Maybe I'll generalize this just a little bit here. Instead of n here, if I have p times n, and this will be p. Oh, it's even harder to understand. Sorry, let's just keep as is. And so much for application problems.